The crosswind landing technique described in most publications is incomplete and can leave false impressions. This video covers the rest of the story. Most pilots are taught that there are two methods to accomplish a crosswind landing, either a slip or a crab. This is not precisely correct. What is true is that these two methods each correct crosswind drift. With one exception, optimum crosswind landing technique utilizes both of these methods together. The advantage of one method can then compensate for the disadvantages of the other. As we will see later, the exception is for airplanes with long wingspans or low engine mounts, which restrict bank angles close to the ground. The crab method is readily understood by all pilots. The airplane is headed into the wind such that when the airplane's velocity through the air is combined with the wind, the air's velocity over the ground, the resulting velocity of the aircraft over the ground is aligned with the center line of the runway. This is illustrated by the familiar wind triangle shown here. The wind correction angle is the difference between the airplane's heading and the direction of the runway center line. It is determined by crosswind speed and the airplane's airspeed. In order to combine the crab and slip into the optimum crosswind landing technique, we have to see what is really happening in a slip so that we can determine its advantages and disadvantages. We will start by defining centripetal force. If a force is applied in the flight path direction, the airspeed will change, but not the direction of travel. An example is when thrust is greater than drag. The difference between the two forces is an unbalanced force, which changes the speed. If an unbalanced force is applied to the aircraft perpendicular to the flight path direction, the direction of travel changes, but not the airspeed. This required perpendicular force is called the centripetal force. It is a combination of all aerodynamic forces acting perpendicular to the flight path. In a normal turn, centripetal force is provided by the horizontal component of wing lift. We will now go to the horizontal force simulator to observe a slip in action. This simulation shows the motion and all of the forces in the horizontal plane acting on a 6,000-pound light twin. Force values are shown in pounds, along with their vectors drawn to scale. Flight path direction is shown in red, and its opposite relative wind is shown in green. This simulator is designed primarily to examine engine-out effects on multi-engine airplanes, but it is also useful in examining forces in a turn. We can make changes by typing new variables in the boxes and then clicking on the label to activate them. Note in the upper left portion of the screen we can change the bank angle, thrust values, airspeed, and percent of rudder deflection. With the thrust and airspeed set at a common approach setting, let's set up a 5-degree right bank angle. Positive values are right and negative values are left. Notice that the centripetal force is provided by the horizontal component of the wing lift. A common question is, it's clear why centripetal force changes the flight path direction, but what makes the airplane turn about its vertical axis? Let's repeat the turn entry and pause the action at the beginning. Note that as the horizontal lift component begins to change the flight path direction, the flight path and its opposite relative wind are now slightly right of the nose. This creates an angle of attack on the tail, which produces a negative or left horizontal lift on the tail. This causes the airplane to begin rotating to the right about its center of gravity. This process will continue until the rate of rotation of the airplane matches the rate of rotation of the flight path. When this occurs, the nose will be aligned with the flight path and no further tail lift is required. We will now continue the action in order to watch this occur. Next, let's make a similar turn with rudder deflection. We will now apply 26% right rudder and sufficient left aileron deflection to cancel out the roll stability that is trying to create a right bank angle. Notice that the relative wind is now coming from the left side, creating an angle of attack on the fuselage. This angle of attack is called the side slip angle. This produces fuselage lift, which is perpendicular to the relative wind. Think of the fuselage as a thick symmetrical wing with a very short span turned on its side. The combination of fuselage lift, tail lift, and horizontal components of thrust provide the centripetal force that creates the turn. Note that this centripetal force is approximately the same as the value created by a 5-degree bank angle and produces the same rate of turn. So, what will happen if we now apply a 5-degree bank angle in the opposite direction? We now see that the horizontal component of wing lift cancels all of the forces created by the rudder deflection, making the centripetal force 0 and stopping the turn. We are now looking at a slip. In the slip, we are flying sideways through the air, which allows us to cancel a crosswind while keeping the landing gear aligned with the runway centerline. Note that a slip requires a constant rudder deflection and a constant opposite aileron deflection. Also, because of the angle of attack on the fuselage, drag is increased. Let's see how we can apply this information to a practical crosswind landing. This picture shows that both the crab and slip method must correct for the crosswind with the same wind triangle. Therefore, the side slip angle must equal the crab wind correction angle. Before we can combine these two methods into the optimum crosswind landing procedure, we have to examine their relative advantages and disadvantages. Unfortunately, the slip method has many disadvantages. Cross-control flight can be difficult. The added drag affects approach speed and approach stability. Airspeed accuracy and stall speed can be changed by sideways flight. And if an inadvertent stall should occur, sideways flight can lead to a spin. A slip can be uncomfortable for passengers and increases their anxiety. Slips require large cross-controlling at higher altitudes where wind speeds are greater. And rudder effectiveness limits the amount of crosswind that can be corrected. In addition, cross-controlling limits turbulence correction by restricting full control deflection. A slip's only advantage is that wheels are aligned with the direction of travel. The crab method has only one disadvantage. The wheels are not aligned with the direction of travel. Its advantage is that a crab is a normal flight maneuver that does not involve cross-controlling. Another advantage is that it can cancel any crosswind. A slip correction has many disadvantages except at heights close to the ground, while the crab method's only disadvantage is just before touchdown. Therefore, the best crosswind correction technique is a combination of the two methods, where a crab is used until shortly before touchdown, and then a precision transition to a slip is accomplished. Let's examine the precision transition more closely. The precision transition involves yawing the nose toward the runway centerline at an amount equal to the wind correction angle. In the same time period, the wings must be banked a precise amount in the opposite direction in order to establish a side slip angle equal to the original wind correction angle. The precise slip bank angle is directly related to the side slip angle and is therefore directly related to the crab wind correction angle. We can now use the horizontal force simulator to find this relationship. Let's look at several crosswinds. At our approach speed of 90 knots, the 10-knot crosswind requires a wind correction angle of 6.3 degrees. Since the slip requires the same 6.3 degree side slip angle, let's go to the horizontal force simulator to find the required bank angle and rudder deflection. Selecting a 4.4 degree bank angle and 23% rudder deflection, we see the side slip angle stabilizes at 6.3 degrees. Notice that the bank angle is 70% of the side slip angle. Also notice that the slip bank angle is also 70% of the crab wind correction angle. Now let's look at a 20-knot crosswind. In this case, the wind correction angle is 12.8 degrees. Selecting a bank angle of 8.9 degrees and the rudder deflection of 48%, we see the side slip angle stabilizes at 12.8 degrees. Again, the bank angle is 70% of the side slip angle. The slip bank angle is again 70% of the crab wind correction angle. Now, let's look at a 34-knot crosswind. We will see that this is the maximum crosswind that this airplane can handle with a slip. Selecting a 12.4 degree bank angle and maximum rudder deflection, 100%, we see the side slip angle stabilize at 22.1 degrees. In this case, the bank angle is 56% of the side slip angle. In this maximum slip crosswind correction case, we see that the bank angle is 56% of the crab wind correction angle. Looking at these three examples, we see two important things. First, the given airplane at its approach speed has one exact slip bank angle for each crosswind. Second, this bank angle is slightly more than 1/2 of the crab wind correction angle. Now let's look at the precision transition in detail. A precision transition from a crab to a slip consists of yawing with rudder pressure to align the longitudinal axis with the runway center line, while simultaneously setting the precise slip bank angle with appropriate aileron pressure. During the transition, the increasing side slip angle compensates for the decreasing wind correction angle. This maintains the wind triangle relationship and continues the cancellation of crosswind drift. Remember that there is one exact slip bank angle for a particular crosswind for your airplane and approach speed. For example, if a left wind correction angle of 20 degrees is required on final approach, make the transition to a slip by yawing 20 degrees right while simultaneously banking 12 degrees left. Where to make the precision transition is a matter of pilot preference. It should be accomplished at its lowest height that the pilot is comfortable with. Initially, this may be just before the flare, changing to just before touchdown with additional experience. The advantage of a late transition is that full control deflection for turbulence correction is available almost to touchdown. An analysis of aircraft from small general aviation airplanes to heavy jet transports predicts that the slip bank angle will be between 47% and 80% of the Crab wind correction angle for almost any airplane, with an average value of 68%. Theoretical relationships are not really important, since the relationship between slip bank angle and Crab wind correction angle for a particular airplane can easily be observed experimentally. Assuming that the slip bank angle is 1/2 of the Crab wind correction angle is a good initial assumption. Keep in mind that the visual relationship between these two angles is far more important than their exact numerical relationship. The Crab wind correction angle is estimated visually, and a visual picture of the required slip bank angle is based on this estimate. These pictures compare the visual crab angle and the visual side slip bank angle. Knowing that there is a specific slip bank angle associated with the crab angle forces us to look for it, allowing this visual relationship to be learned with minimal crosswind landing experience. The learning process may be sped up by measuring the crab angle by comparing heading with runway direction, and then banking half of this angle and memorizing the visual bank attitude. This light airplane is on final approach, correcting for a left crosswind with a crab angle. The precision transition is accomplished by yawing to line up the longitudinal axis with the runway center line, while simultaneously establishing the precise slip bank attitude. Let's summarize by examining a crosswind traffic pattern. The required crab angle on downwind leg and the perceived ground speed on base leg are the first crosswind indicators. They allow us to begin the turn onto final approach earlier or later than normal, and to roll out on the runway center line with an estimated crab angle already established. After executing a precision transition and establishing the slip bank attitude, we expect that friction will decrease the wind speed just before touchdown, so we will decrease the slip bank attitude by half while reducing the slip rudder pressure just before the wheels touch. After touchdown, reduce rudder pressure to straighten the nose wheel while keeping aileron deflection into the wind. After the nose comes down, maintain directional control with rudder and differential braking to compensate for weathercocking into the wind. What if the crosswind exceeds the slip ability of the airplane, which is limited by rudder authority? Strong crosswinds beyond slip limits require a crab angle until just prior to touchdown. Then a decrab maneuver is needed to align the wheels with the direction of travel just before the wheels touch. This is accomplished by yawing with rudder pressure while maintaining bank attitude with opposite aileron pressure. The amount of yaw required can be minimized by initially entering a slip at less than maximum rudder deflection, so that adequate rudder deflection is available for the decrab prior to touchdown. For example, a left 30-degree wind correction angle is being held on final approach. Just before flare, establish a slip by yawing 10 degrees right while banking 6 degrees left. Then, near touchdown, align the fuselage with the center line by yawing 20 degrees further right while maintaining the left 6-degree bank angle with aileron pressure. This decrabbing with rudder pressure immediately before touchdown, where friction reduces the crosswind, allows wheel alignment with the direction of travel before the flight path has time to change significantly. Timing is critical, but the resulting small fuselage lift caused by the yaw takes a relatively long time to change the flight path direction. This technique is especially useful for single-engine airplanes, since they generally have less effective rudder control than multi-engine airplanes with wing-mounted engines, where the control of engine-out yaw is a primary design consideration. We should note that precise decrabbing is not necessary on slippery runways due to light friction side loads. On ice-covered runways, maintaining a crab angle near touchdown allows thrust to reduce downwind drift, but braking force may be nil. Thrust may keep you on the runway, but may make it impossible to stop. Some large transports can drag a wingtip or engine pod at a bank angle of 15 degrees or less, so it is common practice for these aircraft to correct for a crosswind with a crab, and decrab just before touchdown, without a prior partial slip correction. The decrab is accomplished while maintaining the wings level with opposite aileron pressure. The technique is the same as the strong wind procedure just described, except that an initial partial slip is not used. Let's look at a video with this procedure in action. Notice the large right wind correction angle in the crab. Then the left yaw to line up with the center line while maintaining the wings level, followed by landing the nose wheel and rudder corrections to track the center line. In order to make a precise transition from a crab to a slip, we should remember that for a particular airplane at approach speed, there is only one bank angle for each crosswind, and that this bank angle is related to the crab angle on final approach. Knowing the required slip bank angle makes the precision transition possible.